Imagine waking up tomorrow and discovering that every secure digital vault on the planet, I mean, your bank accounts,
Yeah.
those encrypted messaging apps you use, even global financial routing systems, was just silently unlocked by a machine. And not just any machine, but one running on like a handful of manipulated atoms.
Yeah, or imagine a geopolitical crisis that gets completely upended, not by some multi-billion-dollar stealth bomber, but by a fleet of off-the-shelf commercial drones.
Right.
Drones that were modified with open source code somebody just downloaded over the weekend.
It's terrifying. But welcome to the deep dive, everyone. Today we're looking at a roadmap of exactly how those scenarios aren't just, science fiction anymore. They are the imminent reality of the next decade.
Exactly. We are unpacking the Stanford Emerging Technology Review 2026 today.
Yeah.
It's essentially this master document compiled by the top engineering, science, and policy minds over at Stanford. And it's designed to give strategic decision makers a comprehensive layout of 10 frontier technologies.
And what makes this document so uniquely valuable is that it doesn't actually prescribe what you should do about these technologies, right? It just neutrally maps out the blast radius, basically, of how they're all colliding.
Right. It's not a policy manifesto. It's an observation of reality.
And that collision is exactly why we're taking this apart today. Because, I mean, we are constantly slammed with localized hype.
Oh, absolutely.
One day it's a breakthrough in synthetic biology. The next day it's some terrifying new capability in an open weight foundation model. And it is incredibly easy for you to get tunnel vision. But Stanford's data provides, like, the ultimate cheat code here.
It really does.
It's a technically grounded bird's eye view of how these distinct fields are fundamentally altering the global landscape just by crashing into each other.
And, the word crashing is actually the perfect entry point into their central thesis.
How so?
Well, we're entering a technological era that history will probably compare to the electrification of the world or the dawn of the internet.
Sure.
But there's a really distinct divergence this time. Historically, technological revolutions were somewhat linear, right? And isolated.
Like the steam engine.
Right. Progress in steam engines didn't immediately accelerate progress in biology. But today, the acceleration is happening across multiple, highly complex domains simultaneously.
Okay, but I always have this, like, healthy amount of skepticism when people say, oh, this time is different.
Sure, yeah.
Because in tech, everyone always thinks they're living at the apex of history, right? We saw it in the dot-com bubble. We saw it in the smartphone boom. So, I mean, are we just suffering from a massive case of recency bias, or is there a structural reason why the mechanics of innovation have actually changed this time?
It's definitely a structural change. And it's driven entirely by what the authors call convergence.
Convergence.
Right. Progress in one specific field now acts as the literal combustible fuel for entirely separate fields.
Oh, I see.
Take the core loop we're seeing right now. Advancements in artificial intelligence allow us to simulate and discover novel molecular structures in material science and at unprecedented speeds.
Okay.
Then those new materials are used to manufacture vastly superior heat-resistant semiconductors.
Right, which then feed back into the AI.
Exactly. Those advanced semiconductors are racked into massive data centers to train even more capable AI. It's a compounding, closed-loop accelerator.
Wow. And because that loop is spinning so fast, the entire concept of a moat or like a permanent technological advantage completely evaporates, doesn't it?
Precisely. The geopolitical reality has fundamentally shifted here. Technological leadership is now explicitly recognized and wielded as a geopolitical weapon. But the lifespan of any advantage is strictly temporary.
Because everyone else catches up so fast.
Right. Competitors adapt incredibly quickly. The underlying research diffuses across borders before you can even lock it down. So resting on a previous generation's breakthrough basically guarantees you'll fall behind.
Which is wild.
And furthermore, the engine of this innovation isn't the government anymore.
Yeah, that's a big shift.
During the Cold War, or the Apollo era, the state drove the breakthroughs. Today, the sheer volume of capital and the speed required means the private sector absolutely dominates the innovation landscape.
Which introduces a really fascinating dynamic when we look at how different governance systems manage this private sector dominance.
Yeah, the analysis of global governance models in the report is quite revealing on this point.
I found that section really interesting.
Because the data suggests that democracies have a structural advantage in fostering open inquiry. That chaotic, decentralized environment where capital flows freely and unexpected, lateral breakthroughs just happen.
Right, the classic Silicon Valley model.
Exactly. But on the flip side, the report notes that authoritarian states possess a distinct structural capacity to strategically marshal massive amounts of capital.
Because they can just direct it from the top down.
Right. They can direct state-backed focus onto incredibly specific multi-decade goals. They don't have to navigate the shifting priorities of election cycles or quarterly shareholder reports.
So it's the chaotic brilliance of decentralized venture capital versus the sheer brute force of multi-decade centralized industrial policy.
That's a good way to put it.
And what becomes abundantly clear reading this is that having the smartest scientists just isn't enough anymore. I mean, you can have the most elegant theoretical physics paper in the world, but if you lack the raw manufacturing base or the stable institutions or the talent pipelines to physically build the thing.
The science is essentially useless on the global stage.
Right, exactly. Everything relies on this interconnected web of physical and digital capabilities.
And sitting at the absolute center of that web, basically supercharging every other node, is artificial intelligence.
Yeah, AI is the big one.
It has officially transitioned from being just a discrete tool to being the general purpose engine of global scientific discovery.
Because we've moved far past the era of narrow AI, right? Like the algorithms that could only play chess or recommend a movie on Netflix. We are firmly in the era of foundation models.
Yes. These massive architectures are fundamentally reshaping how science is done. And it's critical to look at how they're being deployed.
Yeah.
You have the closed source proprietary models that are locked behind APIs.
Sure.
But increasingly, the geopolitical landscape is being shaped by open weight models.
Where anyone can just download them.
Exactly. The architecture and the billions of parameters are freely available for anyone to download, modify, and deploy locally.
I think we need to talk about the physical reality of what these foundation models actually are for the listener, because the scale is almost impossible to visualize. We treat AI like it's just, magic software floating in the ether.
Right, the cloud.
Yeah, exactly. But the physical footprint required to birth these models is staggering.
The numbers in the report are extraordinary. To train a model at the capability scale of a GPT-4, you were looking at deploying roughly 25,000 highly advanced GPUs.
25,000.
And these aren't consumer graphics cards that you put in a gaming PC. These are massive, specialized processors. And they have to run at maximum capacity continuously for about 100 days.
That is hundreds of millions of dollars in bare metal hardware alone. And that's before you even pay a single engineer or secure the trillions of tokens of training data.
Exactly.
It's like we've decided to build a nationwide utility system from scratch in less than 5 years. We are essentially trying to pipe cognition directly into our grid, just like we pipe in water or electricity. But the plumbing is insanely expensive.
That utility analogy holds up perfectly, especially when you look at the energy bottleneck. The infrastructure load is split into two distinct phases.
Right.
First, you have the training cost. That's the one-time massive spike in computational brute force required to establish the neural network's weights.
The 100 days of 25,000 GPUs running hot.
Yes.
Yes.
But the true long-term burden is the inference cost.
Okay, explain that.
Inference is every single time a user queries the model, or when an automated system uses it to make a decision. That requires active compute. So as foundational models are integrated into global supply chains and medical diagnostics and logistics,
that inference energy burden scales up infinitely.
Infinitely. It's a continuous, massive draw on the power grid.
But the payoff for that energy burn is already showing up in ways that go far beyond just, writing code or generating text emails. The application layer is where this gets wild.
Right. A perfect example highlighted in the data is computer vision in agriculture.
Oh, this blew my mind.
AI-powered weed detection systems are now capable of analyzing crops millimeter by millimeter in real time.
Well, attached to a moving tractor, right?
Exactly. And they trigger microbursts of herbicide only exactly where needed. The report demonstrates reductions in chemical usage by up to 90%.
90%?
Yes, that fundamentally alters the economics, the supply chain, and the environmental footprint of global agriculture.
It's incredible. But with that capability comes the reality of what happens when we wire these probabilistic systems into critical infrastructure.
Right, because they aren't perfect.
No. They are, at their core, prediction engines. They suffer from hallucinations. They confidently invent false information. We see adversarial attacks where, like, a few imperceptible pixels changed on a physical stop sign can cause an autonomous vehicle's vision system to classify it as a speed limit sign.
Which is terrifying. And this is why the geopolitical competition isn't just about who has the cleverest chatbot.
Right.
Nations are locked in a fierce contest for the underlying control structures of the technology itself. We're seeing a race to define the global standards, the interoperability frameworks, and the raw compute capacity.
Because whoever builds the rails controls the train.
Exactly. If your nation controls the foundational standards of AI deployment, you exert immense geopolitical gravity over everyone else who adopts them.
But all of this abstract geopolitical maneuvering crashes into a very hard physical wall. I mean, you can't run 25,000 GPUs, and you can't build massive data centers without the most complex physical objects human beings have ever engineered, which pulls us directly into the paradox of semiconductors.
Semiconductors are the absolute bedrock. If convergence is the engine, silicon is the roadway.
Yeah.
Without advanced chips, the entire AI boom simply stops. The dynamics here are fascinating because the global supply chain is incredibly asymmetric.
Right. It's very lopsided.
Take the United States, for instance.
Mm.
It maintains an overwhelming dominance in chip design. That's the complex architecture of how these billions of transistors are laid out.
The blueprints.
The blueprints, exactly.
Yeah.
But there's a glaring systemic weakness in actual fabrication capacity.
And this is where I want to challenge the prevailing narrative a bit, because if you look at the raw numbers, the U.S. government and the private sector are throwing hundreds of billions of dollars at this. We have the capital.
Tons of capital.
So if Taiwan's TSMC can build these fabs in Hsinchu, it defies logic to a lot of people that the U.S. can't just brute force its way out of this bottleneck. Why not just build a dozen fabs in Ohio or Arizona? What exactly is Taiwan doing that $1 trillion US can't replicate overnight?
It's because building a cutting-edge fab is emphatically not a capital problem. It's an ecosystem problem.
An ecosystem problem.
Right. These facilities represent the most precise manufacturing tolerances in human history. We are talking about manipulating extreme ultraviolet light to etch patterns onto silicon at the atomic scale.
It's literally atom by atom.
Exactly. You cannot just stand up a building and turn on the machines. You require a hyper-specialized talent pipeline. Engineers, material scientists, and technicians who possess decades of tacit, hands-on knowledge.
It's the invisible infrastructure.
Yes, the invisible infrastructure. You need the chemical supply chains for ultra-pure gases. You need the advanced packaging facilities, the specialized optics.
All in one place.
Right. It takes billions of dollars in 3 to 5 years just to construct the shell of a modern fab. But it takes generations to build the surrounding intellectual and industrial ecosystem to keep yield high enough to actually be profitable.
Wow. And meanwhile, the demands of AI are forcing the architecture of these chips to evolve rapidly anyway. We are hitting the thermal and physical limits of moving electrons through copper wire.
Which is driving the shift toward photonics.
Right.
Literally using light to transfer data between chips. It generates far less heat and offers massive bandwidth increases. But again, that requires entirely new manufacturing paradigms.
This immense complexity directly informs the strategic posturing we see globally. And Stanford's analysis of technology export controls, specifically the strategies aimed at restricting China's access to the most advanced lithography machines and high-end AI chips, it highlights a really critical unintended consequence.
They describe it in the report as the containment paradox.
The containment paradox. How does the report define that?
Well, they note that in the short term, utilizing export controls and strict technology embargoes absolutely succeeds in denying a competitor the compute capacity needed to train frontier AI models.
It slows them down.
It buys you time. However, the paradox is that this exact same friction acts as an incredible evolutionary pressure cooker.
By forcing their hand.
Precisely. The report observes that by completely cutting off access to the global supply chain, you forcefully incentivize that competitor to decouple entirely. And they pour limitless state resources into achieving total long-term self-sufficiency.
It's a classic short-term tactical victory that potentially funds the creation of a completely independent, parallel, and highly resilient technological ecosystem in the long term.
That is the precise strategic trade-off the analysis highlights. It's not a simple win.
Okay, so we have the silicon to process the data, and we have the foundation models to synthesize it. But how does that digital intelligence actually interact with the physical world?
That's the big hurdle.
Because right now, a GPU just sits in a climate-controlled server rack. To impact physical reality, you have to cross the digital-physical divide. Which brings us to the stubborn, frustrating frontier of robotics.
Robotics is perhaps the most brutal discipline in engineering because it is ruthlessly unforgiving.
Yeah.
It's not a single field. True autonomy requires the perfect, real-time integration of sensors, computer vision, actuators, advanced materials, and control theory.
So many moving parts,
Yep.
literally.
Exactly. If the software is perfect, but the mechanical actuator has a millimeter of unexpected friction, the entire system fails.
This highlights the most mind-bending contrast in modern tech for me. We just established that an LLM is trained on trillions of text tokens, essentially the entire scraped written history of humanity. It has practically infinite data,
Right.
but a robot operating in physical space, it might only have tens of thousands of real-world episodes to learn from.
Because the physical world refuses to be perfectly simulated. This is more of X paradox in action.
More of expert.
Yeah. High-level reasoning requires very little computation for an AI, but low-level sensory motor skills like tying a shoelace or walking across a gravel driveway require immense computational resources.
So backwards from how humans learn.
Right. Gathering data in the digital realm is frictionless. Gathering data in the physical realm is incredibly destructive and slow.
I like to think of it this way. It's like an LLM is a brain in a jar that has read every single physics textbook in existence. It perfectly understands the math, gravity, friction, and mass.
Okay.
But a physical robot is like a toddler. It
Okay.
doesn't matter how many textbooks the toddler read. It has to physically trip over the living room chair 100 times, scrape its knee, and physically feel the floor to actually internalize the physics of balancing its own weight.
That is the exact bottleneck to generalized physical autonomy.
Huh.
I love that analogy. If a foundation model hallucinates in training, it just adjusts a weight and a matrix. Nobody gets hurt. But if a bipedal robot miscalculates friction during reinforcement learning, it falls over, shatters a $100,000 LiDAR sensor, and a human engineer has to physically walk over, repair the hardware, and manually reset the physical environment.
The downtime is massive. But despite that friction, we're seeing immense capital flow into humanoid robotics, especially for, like, logistics and healthcare.
The promise is massive,
Yeah.
but the deployment reality is gated by battery density, the inefficiency of electric actuators compared to biological muscle, and of course, immense safety regulations.
Sure, you don't want a 200-pound robot crashing into a nurse, but there is one theater where safety regulations and delicate testing are completely bypassed, and where physical autonomy is already rewriting the rules of human conflict.
Yes, the battlefield.
Right.
The analysis of modern warfare in the report, particularly looking at the dynamics in Ukraine, shows a permanent shift away from exquisite, highly expensive legacy hardware.
The big tanks and jets.
Right. The battlefield is now dominated by cheap, highly autonomous, mass-produced drones.
You have multi-million-dollar armored columns being neutralized by modified consumer racing drones carrying retrofitted munitions. It is a complete inversion of the military-industrial cost curve.
It is the democratization of precision strike capabilities. And it's driven entirely by the convergence of cheap sensors, open-source control software, and widely available commercial manufacturing.
It's terrifying because it shows how quickly the manipulation of physical space can scale once the rules are off.
Absolutely.
And if robotics is the mechanical manipulation of the macro world, our next domain is the manipulation of the very building blocks of reality itself. We are moving from silicon and steel to synthetic biology and materials science.
This is where the concept of convergence reaches its most profound level. The analysis frames synthetic biology not just as a medical tool, but as a general-purpose manufacturing platform.
That phrase is so heavy. General-purpose manufacturing platform.
You are crossing a threshold where humanity is actively moving beyond biological inheritance.
I really want to dig into the mechanics of this because it sounds like pure science fiction to a lot of people. The claim is that if we can encode a biological pathway into DNA, we can effectively grow it at scale.
Yes.
We aren't just talking about engineering drought-resistant wheat, are we? We are talking about literally programming yeast or bacteria to manufacture novel polymers, industrial chemicals, even self-healing building materials. How does that leap from a tiny petri dish to a massive industrial refinery actually work?
It works by treating the biological cell as a programmable microfactory.
Okay.
Through CRISPR and advanced gene editing, you aren't just tweaking existing traits. You are inserting entirely new synthetic metabolic pathways into a microbe.
Like writing new code into it.
Exactly like that. You then put that engineered microbe into a massive industrial bioreactor. You feed it basic sugars, and it excretes the exact complex molecule you programmed it to make,
Wow.
whether that's a precursor for a pharmaceutical drug or an advanced carbon-negative plastic.
But finding those specific pathways used to take decades of trial and error in a lab, right?
Decades. And that is exactly where AI convergence changes everything. We are now using AI to predict how proteins will fold and to simulate how entirely new theoretical materials will behave before a single drop of liquid is ever synthesized in a physical lab.
It completely cuts out the trial and error.
Right. Material science is the silent driver behind every other breakthrough. If you want a better semiconductor or a lighter drone battery or a biologically compatible neural implant, it all requires novel materials.
But the strategic landscape here is deeply concerning when you read the report. The data shows a massive asymmetry in how different nations are approaching this biomanufacturing revolution.
The warning in the text is quite stark.
Yeah.
They note that China has spent decades meticulously constructing strategic, state-backed biotech capacity, basically treating it as foundational infrastructure.
Like building highways.
Yes. The United States, conversely, has relied almost entirely on the decentralized investments of the private sector. The explicit warning in the report is that this lack of coordinated national strategy risks a severe loss of biotechnology sovereignty.
They actually use the phrase Sputnik-like surprise in the text.
Yes, they do. Meaning the strategic shock of waking up and realizing a geopolitical competitor has achieved an undeniable foundational capability in biomanufacturing or biodefense that your own domestic supply chain is entirely unequipped to match.
And scaling up those massive bioreactors alongside scaling up the AI data centers and the fabrication plants, all of this requires a staggering, mind-numbing amount of raw power, which slams us face first into the physical limits of our grid and the energy trilemma.
Energy is the master resource. Without it, the entire frontier tech ecosystem collapses.
So what is the energy trilemma?
The energy trilemma refers to the brutal three-way tug-of-war facing every modern economy. You need energy to be three things: highly reliable, broadly affordable, and low in emissions.
You can usually get two, but not three.
Exactly. Achieving all three simultaneously at the scale required by these converging technologies is the defining engineering challenge of our time.
It's fascinating to look at how Stanford analyzes the shifting political landscape around this trilemma, because the rhetoric is definitely evolving right now.
It is. The analysis neutrally points to a distinct shift in U.S. political and industrial framing.
Right.
The document outlines that the overarching narrative is moving away from a strict, exclusive focus on climate urgency, and it's pivoting heavily toward a framework of energy dominance and national security.
Interesting. And practically, what's that look like?
Well, the report observes that this manifests as a renewed emphasis on maximizing existing fossil fuels and rapidly expanding advanced nuclear fission, simply to guarantee that reliability and affordability aren't sacrificed, while the momentum for global renewable deployment faces extreme supply chain friction.
Just to be clear for you listening, we're not endorsing that shift one way or the other. We're just reporting what the Stanford data is observing in the policy space.
Yes.
But we constantly see the headlines about incredible green breakthroughs. Just last month, there was another story about a fusion reactor achieving net positive energy. If the physics are actually being solved in the lab, why does the report say the real-world energy transition is so agonizingly slow?
It comes down to a concept called infrastructure inertia.
Infrastructure inertia.
Right. There is an oceanic gap between demonstrating scientific feasibility in a magnetic confinement chamber for a fraction of a second and the brutal reality of overhauling the planet's physical power grid.
We are still pushing electrons through copper wires strung up on wooden poles.
Exactly. The existing infrastructure is massive. It's deeply entrenched, and it represents trillions of dollars of sunk capital. Yes, we are seeing rapid, fragmented innovation in deep geothermal solid-state batteries and small modular nuclear reactors.
The tech is there.
The tech is emerging, yes. But taking a novel energy source and integrating it seamlessly into a legacy grid requires staggering industrial policy and requires decades of capital expenditure and the physical mining of millions of tons of copper, lithium, and rare earth elements. You cannot just software update a physical power grid.
That's a great point. So the physical grid is the visible infrastructure we interact with every single day. But there is a completely invisible mathematical infrastructure holding the entire global economy together. And it is facing an existential clock. Let's move into quantum technologies and the impending cryptography crisis.
This is one of the most urgent sections. Modern digital life operates entirely on the assumption that certain mathematical problems are practically impossible to solve.
Right.
Every secure message, every banking transaction, every piece of classified state data relies on cryptographic protocols like RSA.
But a fully fault-tolerant quantum computer doesn't care about our classical assumptions, does it? The timeline they project in the report is terrifying. The data suggests that standards like RSA 2048 could be completely compromised within 5 to 15 years.
Which is tomorrow.
That isn't a theoretical problem for our grandchildren. That is tomorrow in infrastructure time.
I want to really unpack how this works, because a quantum computer isn't just a really fast regular computer,
Ooh,
right?
not at all. It is a completely different paradigm of computation. Classical computers process information in binary bits, ones and zeros.
Okay.
If a classical computer wants to guess a cryptographic key, it basically has to brute force its way through billions of combinations, one by one.
It's like a thief standing in front of a massive steel bank vault, just spinning the dial, hoping to randomly hit the one correct combination out of a trillion. It would take the lifetime of the universe to crack.
Exactly. But a quantum computer uses qubits. And qubits can exist in a state of superposition, meaning they represent complex probabilities of both 1 and 0 simultaneously until they are measured. My brain always hurts trying to picture that.
That defies macrophysics. But when you apply something called Shor's algorithm to a quantum machine, it doesn't try every combination. It uses quantum interference to find the prime factors of massive numbers almost instantly. It's essentially a mathematical backdoor.
So the thief doesn't bother with the volt dial at all. They just walk straight through the wall.
That's the threat. That's exactly it. However, the engineering reality of actually building a machine capable of executing Shor's algorithm at scale is incredibly daunting. Qubits are absurdly fragile.
Because of environmental noise.
Right, they suffer from decoherence. The slightest environmental noise, a fluctuation in temperature, a stray cosmic ray, even ambient electromagnetic fields from a nearby elevator will cause the quantum state to collapse, instantly destroy the calculation.
Which is why we hear about error correction taking up an insane amount of the system's resources.
Yes. Think of a qubit not as a coin resting flat on a table, but as a coin spinning constantly on its edge. The machine's job is to extract data from that spin. But if the table vibrates even a fraction of a millimeter, the coin falls flat.
And the data is gone.
Gone. Because of this extreme sensitivity, upwards of 90% of a quantum computer's processing power must be dedicated purely to quantum error correction.
90%.
Yeah, basically surrounding the few useful qubits with thousands of other qubits just to constantly monitor and stabilize the local environment.
It's a monumental physics problem. Now, looking at how the financial world is reacting to these digital paradigm shifts, the analysis of U.S. policy on digital currency is quite revealing.
Yes, the market observation here is really interesting. The report neutrally notes that the U.S. has distinctly leaned away from developing a centralized, state-controlled central bank digital currency, or a CBDC.
Which a lot of other countries are pursuing.
Right. Instead, the document observes that the U.S. approach heavily favors private market dynamics, relying on privately issued stablecoins that are backed by fiat reserves to maintain global dollar dominance in the digital space.
Again, just reporting what the analysis observes. But okay, so the U.S. is letting the private market dictate digital currency architecture. What about the actual quantum hardware race? Where does the geopolitical advantage lie today?
Currently, the data shows the U.S. holding a distinct ecosystem advantage in quantum hardware, specifically in things like superconducting circuits, trapped ions, and neutral atom architectures.
And why is that?
Well, this isn't an accident. It is the direct downstream dividend of the massive post-WWII basic research infrastructure, the deep integration between national labs, universities, and venture capital.
But as we established in the convergence thesis earlier, that advantage is inherently fragile, isn't it?
Highly fragile. Maintaining that edge requires uninterrupted access to international graduate talent, and it requires completely secure supply chains for the incredibly rare isotopes and cryogenic materials needed to cool these systems to near absolute zero.
It's so resource intensive. We are pouring billions into unlocking the profound mysteries of quantum mechanics. Yet, arguably, the most profound mystery in the universe is sitting right inside our own skulls.
Yes, the human brain.
Let's look at the reality check happening in neuroscience.
Neuroscience is portrayed as the ultimate frontier, but the report shows it is deeply fragmented. The data categorizes it into three distinct pillars.
Okay, what are they?
First is neuroengineering, which encompasses the highly visible brain-machine interfaces. Second is neurohealth, which is the agonizingly slow battle against neurodegeneration and aging. And third is neurodiscovery, the foundational quest to understand how cognition, memory, and consciousness actually emerge from wetware.
I think we need to confront the massive gap here between the public perception of neuroscience and the scientific reality outlined in the report.
It's a huge gap.
Because we all see the viral videos. We see a paralyzed patient with a neural implant controlling a robotic arm or moving a cursor to play video games. The media portrays it as if the cyberpunk future has fully arrived today.
And this is where the experts deliver a very harsh dose of reality. The progress in neuroengineering is genuinely incredible, but we have to understand what is actually happening fundamentally.
Right.
We are getting very good at placing localized electrodes into the motor cortex to read the electrical spikes of intent. So move arm left, move arm right.
It's like tapping a telegraph wire.
Exactly. It's basic signal processing.
Hmm.
But our systemic understanding of the brain, how a memory is actually encoded, how Alzheimer's systematically dismantles a neural network, or how a complex thought even forms, remains a massive, highly opaque black box.
We just don't know.
We don't. The Stanford experts explicitly warned that the public excitement around brain chips vastly, dangerously exceeds our scientific certainty about the organ itself.
And that hype cycle creates a vacuum for misinformation, right? And predatory claims about curing everything tomorrow. Furthermore, there's a serious geopolitical drift happening here. The report says U.S. leadership in fundamental neuroscience is actually slipping.
It is slipping. And it's primarily due to a lack of long-term, sustained strategic funding, especially compared to foreign competitors who are aggressively scaling up massive, centralized brain mapping initiatives.
Oh, wow.
There is also a complex ethical asymmetry here. Different nations have vastly different regulatory and ethical thresholds for testing invasive neural implants on human subjects, which obviously skews the pace of global neuroengineering deployment.
It is remarkable to think that we literally have a better map of the cosmos than we do of the human brain.
It's true.
Which brings us appropriately to the final physical domain, space, and this concept of the finite commons.
Space has undergone a total paradigm shift. It is no longer the exclusive monopolized domain of superpower governments like NASA or Roscosmos.
The Apollo days are over.
Right. The new space economy is entirely dominated by commercial mega constellations and private launch providers.
And the scale of this shift is almost hard to comprehend. A little over a decade ago, in 2014, there were roughly 1,000 active satellites in orbit. Today, we are looking at roughly 11,000, with active regulatory filings suggesting we could see tens of thousands more deployed in the next few years.
Which introduces the critical strategic concept of low Earth orbit as finite commons.
Meaning there's only so much room up there.
Exactly. It implies that orbital slots and radio frequencies are a strictly limited natural resource.
Imagine discovering an entirely new continent. And for 50 years, it's mostly empty. Just a few highly trained scientists in polite outposts conducting research. Then, almost overnight, it transforms into a chaotic, unregulated, multi-lane superhighway packed with tens of thousands of speeding vehicles, with absolutely no traffic lights, no defined lanes, and no centralized police force. That is low Earth orbit today.
It is dangerously congested, and the physical reality of orbital mechanics makes this an existential threat to future access.
Right, because of the speeds involved.
If two satellites collide at orbital velocities, they don't just fall out of the sky. They shatter into thousands of pieces of shrapnel, which then orbit the Earth at 17,000 miles per hour.
Basically turning into bullets.
Yes. Potentially triggering a cascading chain reaction of destruction known as Kessler syndrome, where the debris destroys more satellites, creating more debris, until orbit becomes completely unusable.
And amidst this rapid commercial congestion, the analysis points out a significant pivot in U.S. space strategy.
Yes, the report observes there has been a massive executive and political pivot toward prioritizing human exploration, putting boots back on the moon and aiming for Mars.
The Artemis missions.
Right. However, the data clearly shows that this pivot has aggressively cannibalized funding and focus away from robotic science missions.
Oh, interesting.
The downstream effect is a severe, highly concerning loss of specialized workforce and institutional knowledge within NASA regarding deep space robotic exploration.
We're losing the muscle memory for the science missions. So we've mapped the board. We've looked at the orbital congestion, the fragile neuroscience frontier, the quantum clock, the energy grid, the biomanufacturing revolution, and the AI engine. When you pull all the way back, undeniable patterns emerge across every single one of these domains.
They absolutely do.
And this is where the Stanford analysis really provides immense value. Let's get into the meta lessons.
Chapter 11. The authors synthesize all this chaos into recurring, structural laws of innovation. And the first major dynamic they identify is the Goldilocks problem of technology governance.
The Goldilocks problem, meaning finding the exact right speed to regulate.
Precisely. If a regulatory body moves too quickly to govern a nascent technology, like synthetic biology or open-weight AI, they operate on bad assumptions.
Because they don't know what it will become yet.
Right. They risk suffocating the innovation in its crib, crippling their domestic industry, and driving the talent offshore to less regulated countries.
But if they move too slowly,
If they move too slowly and wait for perfect safety data, the technology deeply embeds itself into society. The first mover advantage is lost, and an adversarial nation ends up dictating the global standards. Finding that perfect regulatory cadence is nearly impossible.
they also dive into the rhythm of how this progress actually happens, challenging the idea that innovation is just a steady, predictable curve.
Yes, they highlight the reality of nonlinear innovation.
What does that look like?
Well, outside of the highly predictable cadence of Moore's law in semiconductors, almost all scientific progress operates on punctuated equilibrium. You endure decades of agonizingly slow, grinding, seemingly fruitless research.
Followed by a sudden, massive, explosive breakthrough that changes everything overnight.
Exactly. The strategic danger is that modern venture capital and political cycles are entirely intolerant of those slow decades. They underfund the foundational research because it doesn't yield a quarterly return.
And even when you hit that explosive breakthrough, the science isn't safe, you immediately crash into the valley of death.
Ah, the valley of death. This is the brutal chasm between proving a concept works perfectly in a pristine university lab and actually surviving the journey to widespread, profitable commercial scale.
Right.
An AI-discovered material might be theoretically perfect, but figuring out how to manufacture it by the ton, navigating archaic regulatory approvals, and securing the massive patient capital required for physical infrastructure, that is where most incredible breakthroughs quietly die.
And the recurring theme across all these bottlenecks isn't a lack of raw capital or computing power. The ultimate bottleneck, the limiting factor of the entire global innovation system, is human capital.
People are the absolute bedrock. The analysis places immense critical focus on the role of universities here.
Not corporations.
No, corporations are highly optimized for product development, but they generally refuse to fund high-risk, open-ended, foundational research with no immediate commercial application. Universities provide that crucial environment. The data point in the report is stunning. Over 80% of the foundational algorithms deployed globally today originated outside of corporate labs, primarily within academia.
Over 80%, which means if you starve the university system of funding, you are literally starving the pipeline of the future.
Precisely.
And this directly ties into global talent mobility, doesn't it? The ability to attract, retain, and integrate the smartest graduate students from around the world is basically the single most powerful lever of national competitiveness.
It is. And yet, that vital process is constantly derailed by how we culturally digest technological progress. The authors issue a severe warning regarding the hype cycle.
This was such a good section. They use the perfect historical anchor for this. The 1989 cold fusion debacle.
It is the textbook case study. Researchers prematurely claimed to have achieved room temperature nuclear fusion.
Right, which would solve everything.
The media amplified it into an absolute frenzy. Politicians scrambled to align with it. And massive amounts of capital and attention were violently distorted based on pure excitement, completely bypassing the grueling, slow process of rigorous scientific verification.
Which turned out to be flawed.
Exactly. The lesson is that hype is a literal toxin. It forces policymakers to react to imaginary timelines and misallocate critical resources away from the boring, incremental work that actually matters.
Reading this, I realized something terrifying about our current posture. We are so obsessed with inventing the next sci-fi marvel that we are completely blind to how existing tech is being weaponized today.
The report calls this frontier bias, right?
Frontier bias is perhaps the most profound conceptual contribution of the entire document. It is the systemic tendency of governments, investors, and military planners to become pathologically obsessed with the extreme edge of the frontier.
The shiny theoretical breakthroughs. Exactly.
Yeah.
While completely ignoring the massive, world-altering strategic impact of older, mature technologies being combined in creative, novel ways.
It's exactly what we talked about with robotics earlier. We have defense contractors spending billions trying to develop, autonomous hypersonic laser platforms, while the actual war is being won today by a 19-year-old soldier who duct taped a $10 fragmentation grenade to a commercially available toy drone.
That is frontier bias in its purest form. Real asymmetric innovation isn't always about inventing a new fundamental physics paradigm. It is overwhelmingly about creative application, resilient supply chains, and the invisible infrastructure of manufacturing capacity.
So, understanding these meta lessons, the valley of death, the dangers of hype, the reality of frontier bias, how does the collision of all 10 of these technologies fundamentally rewrite the social contract? How does the future actually hit you, the listener?
Chapter 12. The final synthesis consolidates all of this scientific data into 5 massive policy domains that directly impact daily human life: economic growth, national security, health, sustainability, and civil society.
Let's start with the economy. The prevailing narrative is basically a binary. AI either ushers in a post-scarcity utopia where nobody works, or it causes massive structural unemployment. Where does the data point?
The data frames these converging technologies as massive, unprecedented engines of productivity expansion. However, they issue a very specific structural macroeconomic warning.
About Moore's Law, right?
Yes, the global economy has relied on the relentless deflationary cost reductions of Moore's Law for half a century. Computing just kept getting cheaper and faster. But as we hit the atomic limits of silicon and those cost reductions naturally begin to slow down, any long-term economic growth models that rely on computing power getting infinitely cheaper forever might be dangerously over-optimistic.
What about national security? Because walking through this framework today, it feels like every single technology we've discussed is inherently a weapon.
That is the defining characteristic of this convergence: absolute dual-use functionality. A bioreactor that brews a cure for a novel virus can easily be reprogrammed to synthesize a deadly pathogen.
It's the exact same equipment.
Yes. But the most terrifying dynamic the authors highlight is the concept of asymmetric ethical restraint, particularly regarding AI in military command systems.
Like integrating AI into nuclear command and control.
Precisely. The report points out that a democratic nation might impose strict, rigid ethical guardrails, absolutely mandating a human in the loop before a lethal strike can be authorized.
Right.
However, an adversarial nation, prioritizing sheer speed and reaction time in a hypersonic conflict, might completely remove those ethical constraints, allowing the AI to execute autonomous strikes. That creates a massive, highly destabilizing strategic asymmetry.
But the flip side of that danger is health. If convergence is a threat in the security domain, it seems to be the ultimate savior in the health domain.
Health is where the compounding loop of convergence really shines brightest. You are combining the predictive power of AI diagnostics with the atomic precision of quantum sensing, the physical capability of robotic microsurgery, and the biological manufacturing of synthetic biology.
All working together.
The ultimate horizon the analysis points toward is treating aging itself as a curable cellular process. If breakthroughs in neural health can significantly delay neurodegeneration, allowing massive aging populations to remain cognitively healthy and independent.
It would completely alleviate the crushing demographic and economic burden on global healthcare systems.
It fundamentally re-engineers the demographics of the planet.
But finally, we have to look at society and democracy. And this is where the friction is most immediate, I think.
The implications for civil society are immediate and severe. We are facing an environment characterized by the massive erosion of personal privacy, the deployment of unprecedented algorithmic surveillance, and the complete distortion of shared objective reality.
We saw this play out in real time during the 2024 global election cycles. Everyone was bracing for Hollywood-level, completely undetectable deepfakes to manipulate populations.
And what the data shows is that while sophisticated deepfakes were a threat, the informational ecosystem was actually flooded and disrupted by what they call cheap fakes.
Cheap fakes.
Low-quality, easily produced algorithmic manipulations, out-of-context audio, and automated bot networks. You don't need a flawless deepfake to erode democratic stability. You just need enough algorithmic friction to make the population fundamentally doubt everything they see.
Taking all of this in, the 10 domains, the meta lessons, the policy impacts, the ultimate macro-strategic conclusion of this entire document is a complete reframing of how global power works. The defining superpower competition of the 21st century is no longer simply about who commands the largest standing army or who possesses the most aircraft carriers.
No, not anymore. The battleground is entirely about innovation systems. It is about who can rapidly build the underlying compute infrastructure. It is about who aggressively cultivates the global talent pipelines.
Right.
It is about who dictates the standard-setting bodies and who has the deeply embedded physical manufacturing resilience to scale an idea from a whiteboard into 1 million physical units.
Because these technologies are completely inseparable, they are a networked force.
Hmm.
If you have a critical vulnerability in your semiconductor supply chain, your AI foundation models stall. If your AI stalls, your synthetic biology discovery pipeline halts.
Exactly.
If your biomanufacturing halts, your population's health degrades, and your space architecture fails, it is one single, hyper-connected, incredibly fragile network.
That is the ultimate warning of the report. The illusion of isolated technological dominance is over. A single vulnerability in your cybersecurity architecture or your raw materials supply chain can bring the entire national innovation apparatus grinding to a halt.
We have covered an immense landscape today. We've traced the massive physical footprint of the 25,000 GPUs grinding through trillions of tokens to birth a foundation model. We've explored the agonizing physical data bottlenecks of training a bipedal robot, the terrifying vulnerability of the quantum clock ticking down on our encryption, the sheer orbital chaos of 11,000 satellites, and the absolute necessity of recognizing the invisible infrastructure of talent and manufacturing. The Stanford Review is dense, it is sobering, but it is undeniably the clearest map we have to actual levers of power in the modern world.
And before we close, there is one final implication to extract from all of this.
What's that?
We spent a lot of time discussing how bureaucratic policy is too slow and how national hardware advantages are relentlessly temporary. Given that the velocity of convergence is only going to exponentially increase, it suggests that the single most vital, resilient innovation system isn't a trillion-dollar fab or a national strategy or a massive university endowment.
What is it then?
The ultimate infrastructure is the individual human capacity for extreme cognitive adaptability. It is your personal ability to ruthlessly unlearn outdated paradigms, to reject the comfort of previous expertise, and to maintain an operational calm while navigating a permanent, never-ending state of systemic flux.
The ultimate bottleneck and the ultimate unlock is you. How will you rewire your own mental infrastructure for an age where reality itself is constantly being re-engineered? Thank you for taking the time to journey with us into the deep end today. Understanding these systems is the only way to avoid being swept away by them. Until next time, stay curious and always question the hype.